Okay, so today we're going to be talking about something called L'Hôpital's rule. Okay, yes, it looks like L apostrophe hospital. Okay, but it's French, so of course it doesn't make any sense whatsoever. So anyway, it's called L'Hôpital's rule. And to start with, I want to talk about something called indeterminate forms. Okay, if we are trying to take a limit where we are approaching a value of f of x over g of x, or if we're taking the limit as we approach infinity of f of x over g of x. And if we directly substitute or we calculate it out where we end up with 0 over 0 or plus or minus infinity over plus or minus infinity, okay, those are called indeterminate forms. Okay, 0 over 0, infinity over infinity. Um, there's much more to it than that. I'm just going to leave it with that. But anyway, if we end up with one of these forms, then we can use L'Hopital's rule. And what that states is uh, if we are taking a limit like this over this and we end up with either of these cases, then we can take the derivative of both f and g and take that limit instead, provided that this limit does indeed exist. Okay, and what I'm talking about here, this is like an informal proof here. Let's say you have the limit of f of x divided by g of x as we approach a. Well, as you can see here, obviously, f approaches 0, g approaches 0 at a. So you'd have 0 over 0. Okay, but if we zoom in or we focus on the tangent lines at a, okay, so tangent lines, that's derivatives, right? You see that we actually have a specific slope divided by a different slope. So now it's no longer 0 over 0, but instead this slope divided by this slope, whatever that may be. And we would actually get the limit there. So that's, like I said, very informal for why this works. Um, but basically what you need to understand is it works, okay? So what we're going to look at here are a few problems that use L'Hopital's rule, okay? So if we are asked to find the limit as x approaches 1 of the natural log of x over x minus 1, okay, we might look at that and we might see, okay, well, I can just directly substitute, right? Okay, I'm approaching a specific value. So let's say I have the natural log of 1 over 1 minus 1. Okay, well, the natural log of 1, I hate to break it to you, is 0, and 1 minus 1 last check is also 0. So we have this indeterminate form 0 over 0. So we can't just directly substitute in. But using L'Hopital's rule, we can take the derivative over the derivative. Okay, so what's the derivative of the natural log of x? Well, 1 over x. Okay, so what's the derivative of x minus 1? Well, hey, that's 1. So now all of a sudden, if I'm taking the limit as x approaches 1, well, hey, I can directly substitute now in. I have 1 divided by 1 divided by 1, which equals 1. So that's actually what this limit equals. Okay? So pretty neat little trick to get out of a jam there. So this works with infinity as well. If I'm taking the limit as x approaches infinity of e to the x power over x squared, well, if you think about it, both of these are, well, this is an exponential function, this is a quadratic function. As we approach infinity, they are both approaching infinity. Okay, so infinity over infinity. That's the other indeterminate form. Okay, so take the derivative. Okay, so the derivative of e to the x is e to the x. Derivative of x squared is 2x. Okay, so now when I try to take the limit, well, e to the x, as we approach infinity, would still equal infinity. 2x, well, that actually also still equals infinity, right? It's a line, it still goes up. So we're still left with an indeterminate form. Not to worry, we can use L'Hopital's rule again. So if we do this another time here, taking the second derivative here, we would end up with e to the x again. But this time, instead of 2x, we just have 2. So the limit as x approaches infinity. In this case, you'd have infinity divided by 2 although that's like a smaller infinity, that is still infinity. Okay, so the limit of this original function would actually equal infinity, or approach infinity, I should say. Okay, if we do this, it still works with more complicated functions here. Okay, here we have the limit as approaches infinity of the natural log of x over the third root of x. Okay, again, you have infinity over infinity to start with. Okay, if you try to plug those in. So take the derivative. Natural log of x would become 1 over x. Okay, the third root of x, remember that's x to the 1/3 power. So when we use the power rule there, you'd get 1/3 x to the negative 2/3. Okay. Now we could just try to blindly take this as the limit approaches infinity. You'd get 0 over 0, or we can just manipulate the equation a little bit. Okay, so what we actually have here is a compound fraction. 1/3 x to the negative 2/3 is actually 1 over 3x to the 2/3 power. So we have a fraction divided by another fraction. So if you just do some basic algebra here, 1 over x times the reciprocal of this, 3x to the 2/3 over 1. Now, if you rewrite it, you have 3x to the 2/3 over x, the first. Okay, knowing your properties of exponents, you would get 3 over x to the 1/3 power. Now, if you take the limit of that as x approaches infinity, you have 3 divided by a really, really big number, which actually would approach 0. Okay, so you could continue to do L'Hopital's rule if you needed to, but just recognize that there's some algebra that makes the problem easier. Okay, so on your own, here's a problem for you to do. Okay, the limit as x approaches pi of the sine of x over 1 minus cosine of x. Okay, go ahead, pause the video and attempt to do that one. Otherwise, gotcha. If you didn't check first, you would have used L'Hopital's rule incorrectly here. If you substitute pi in, you have the sine of pi over 1 minus the cosine of pi, which is 0 over 1 minus negative 1, which is 0 over 2, which is not an indeterminate form. Okay, that's just 0. So you don't even have to use L'Hopital's rule here. Okay, so make sure that when you check first that you need to have an indeterminate form before you even use L'Hopital's rule to begin with. Okay, so just be careful with that.